Welcome back. We are going to discuss our final two topics really, in this chapter. So we're going to start off by talking about gas density. The formula for gas density isn't different than any other sort of density formula. Remember that the formula for density is density equals mass over volume. That is a big V. That's not little v. We are talking about big V, so we're talking about volume, not velocity. So density is mass over volume. The only big difference between, let's say, for example, a gas density and a liquid or a solid density is that liquid and solid densities are measured in grams per milliliter, but gas densities, because gases are so not dense, they are measured in grams per liter. That's kind of the biggest difference. But we can use this relationship to solve for things. Let's check it out. So let's say that we want to calculate the density of nitrogen gas at STP. So we don't really have any sort of information here, do we? I mean, we know that we want to calculate the density of the mass over the volume, but I don't have the volume and I don't have the mass. I know I'm dealing with nitrogen, so what should I do? Well, since we're dealing with gases, we can take some assumptions. Let's just assume that we have 1 mole of our substance. And if we assume that we have 1 mole of our substance, then we know a lot of stuff, right? If we assume that we have 1 mole, then we know that the temperature at STP is 0 degrees Celsius. We know that the pressure is whatever pressure it is, either 1 atmosphere or 760 millimeters mercury. But most importantly, if we assume that we have 1 mole and we're at STP, then that means our volume now can equal 22.4. Because remember that at STP, for every 1 mole of a gas, we have 22.4 moles, or excuse me, liters of that gas. So now we can take, let's think about another thing. We got to figure out mass. So we know what we can do for liters, right? So we have that 22.4 because we know that for every 1 mole we have 22.4 liters. For every 1 mole, how many grams of nitrogen do we have? Well, we could use molar mass. If we assume that we have 1 mole, then we can figure out molar mass from the table. That's 26.0 grams of nitrogen per 1 mole, right? So we can use that assumption as well. So if we take that 26 grams, then we have what we need. We have grams over liters, which if we shoot that out, we get 1.25 grams per liter. So we do a lot of assuming, but it does help us kind of figure out what we need, as long as we're at STP. But what if we're not at STP, like we see here at number 2? Calculate the density of carbon dioxide gas at 20 degrees Celsius and 107 kPa. All right, so let's keep that equation in mind that we're looking for. Density equals mass over volume. So we can figure out the mass, again, by assuming that we have 1 mole. So we're just going to continue to do that again. We're just going to assume that we have 1 mole. And if we assume that we have 1 mole, that makes the mass really easy. Because the mass we can figure out, we do the molar mass of carbon dioxide, and we should get about 44 grams per 1 mole. But we're still looking for the volume. So let's see, now that we know we have moles, and we also have temperature, and we also have pressure, and I'm not at STP, well then I can use my ideal gas law, can't I? If I take my ideal gas law, which is PV equals nRT, and I convert it to solve for V specifically, so that's nRT over P, well then I have everything I need. So let's take a second and try that out. We kind of have 2 different ways that we can do this really. We could use the ideal gas law, right? So if we solve for the ideal gas law, let me kind of show you both ways. If we solve for the ideal gas law, we would plug in 1 mole on the top. We would plug in the R constant. You're welcome to, again, what is that, liters times, that's kPa. You're welcome to convert into atmospheres if you want. I'm just going to use the value for kPa, makes it easier. So I take all this and I divide that, I should find that I get 22.8 liters. Now, if I were to plug this below, 44 grams divided by 22.8 liters, I should find that I get a density of about 1.93 grams per liter. But there is another way that I can do this. I'm going to do this in a different color. I could also take the grams and I could relate the volume given at STP, because remember, I can always say like, well, what if I was at STP, right? So if I was at STP, I would assume I have 22.4 liters. And then I can assume that a change is occurring, right? Like I'm going from STP and I'm converting from STP into the value shown. So if I go from STP, which is 0 degrees Celsius, to 20 degrees Celsius, I would say that my temperature has gone up. So if my temperature goes up, my volume should go up. So I would set up a ratio that shows that. 293 Kelvin over 273 Kelvin. And then I could also do the same thing for pressure. So I'm going from 101.3 kPa up to 107. So that means my pressure goes up, which means my volume should go down. And I bet you that if you plug that into your calculator, you should still get 1.93. So it just kind of depends on the way that you're comfortable with. You could really do it one way or the other. So that's how you do it. Let's try a little bit on our own here, and then we can go from there. So let's calculate the density of xenon gas at 15 degrees Celsius in 1 atmosphere. So let's actually kind of do this to compare. Let's first figure it at STP. So let's first figure out the density of our substance at STP first, and then let's figure out our substance at these different values. And we can kind of compare them. That might be kind of nice to do. Let's try it out. Go ahead and pause, give it a shot, try and figure out the density of xenon at STP first, which should be pretty quick, and then try and find out the density of xenon not at STP, but at these values shown here. Come on back when you're done. Okay, so that's what you do. When you're at STP, it's really easy. You just take the grams and divide by 22.4. But when I'm not at STP, what I did is kind of like what I did in the previous problem, where I took that STP value and I just evaluated how the change in temperature would affect that volume. If my temperature went from 0 degrees, which is at STP, up to 15 degrees, my temperature would go up, which means my volume should go up, and then that's what I get, 5.54. The thing that's kind of interesting about this is that notice that at lower temperatures, for example, like at STP, at lower temperatures, our density is greater. It's kind of something that's pretty curious. At higher temperatures, our density is lower. Why do you think that might be? Maybe think about it. Maybe we'll talk about it. All right, let's look at number 4. A gas has a density of 3.17 grams per liter at STP. What is the molar mass? Oh, so this time we are looking for molar mass. Remember that molar mass is grams over moles. So we are given a density this time of 3.17. And we would probably want to figure out the mole or the mass of the object first, and then we can kind of probably go from there. So go ahead and give it a try. We're at STP. See if you can kind of work your way through this equation here to see if you can figure out the molar mass. Come on back when you're done. Hopefully you were able to kind of deduce that this was what you're supposed to do. If I were to solve for mass, then it actually kind of works out for me. My liters are going to cancel out, which means that the only thing left in my answer is grams per mole, which is exactly molar mass. So that's molar mass, grams per mole. As easy as that. As long as I'm at STP, I just multiply the mass times the volume together. If I wasn't at STP, this would be a little trickier. I would have to figure out the amount of moles. Okay? We'd probably need a little more information for the problem in order to do that anyways. So that's density. Let us talk about one more little topic before we're done here. Let's talk about mole fraction and partial pressure. So mole fraction is represented with this symbol that kind of looks like a curvy X. It is the Greek letter chi or chi. I'm not sure actually how to pronounce it. I don't know if it's chi or chi or shy. I don't know, I gotta look it up. Anyway, it's like kind of a squiggly X. But what the mole fraction means, it's the ratio of moles of one substance compared to the total moles of the overall equation. So the way that we look at this, the formula for mole fraction is kind of like this. So like you take the mole fraction of a substance is equal to the moles of that substance divided by the total moles of everything involved. So it's kind of like percentage almost. Like it's the fraction or the percent amount of moles of one substance compared to everything else. Again, it's not exactly a percentage, but it is sort of like that. It's like an amount, a quantity of a small piece of a whole is what I'm trying to say. So then this kind of relates to this idea of partial pressure, which we've talked about a little bit in the past, but mole fraction can relate to partial pressure as well. We can use mole fraction and partial pressure to relate the pressure of one gas to a mixture of all the gases. So we can kind of take Dalton's theory a little bit and manipulate it, where if we are looking for the pressure of a single gas, we could take the total pressure of everything. We're not talking about PT like pressure of gas T, we're talking about the total pressure. And if we take that total pressure and we multiply it by that particular gas's mole fraction, we can find out the pressure of that gas in particular. This is not as complicated as it might sound. It's really just like dealing with percentages. So let me show you how this works. Let's say that we have a container that contains 1 mole. Let's say that's 1 mole, excuse me. Container has 1 mole of neon, and it has 2 moles of helium. If the total pressure is 900 torr, what is the partial pressure of each gas? So the first thing we would want to do is we'd want to figure out the mole fraction for each. So you'd figure out the mole fraction for neon, and you'd figure out the mole fraction for helium. So let's kind of look back at that equation that we saw before. We saw that it was the total, or the moles of just that individual thing, divided by the total moles of the entire situation. So how many individual moles of neon are there? There's only 1. So there's only 1 mole. And how many total moles are involved in this entire problem? Well, 1 mole plus 2 moles. That's not very hard, is it? That's 3 moles. Same thing for helium. If we have 2 moles of helium, and then we have 3 moles total, we just divide these, divide these numbers, and we get 3.33 for 1 mole fraction and 6.66. So in order for us to find the partial pressure of each, we would just multiply these values by the total pressure that's given in the problem, 900 torr. And we would end up with 300 torr for this one. And you have kind of 2 choices here. You could either take the 300 torr and subtract it from the 900 torr to find the other one, or you could just kind of do the same thing. Because remember, these are like percentages. We are looking for pieces of a whole, so they have to all add up to the total. And it's really just as easy as that. That's how you use mole fraction. Total moles are divided by the partial moles, multiply it by the total pressure. As easy as that. Let's look at another one. We say a mixture of gases contains 3 grams of neon and 6 grams of argon. The total pressure of the 2 gases is 120 kPa. What is the partial pressure of each gas? So this time we're in grams first, and we're asked to find partial pressure of each. So it's a little trickier. Why don't you pause, give it a try, see if you can kind of manipulate and use the same sort of techniques that we used last time. But remember that you're starting in grams. You can't just go straight from grams into partial pressure. You need to get into moles first. So go ahead and just give it a shot. Come on back when you're done. Okay, so this isn't exactly a hard process, but it might just take a little time. Start by taking the grams of neon and argon. I convert those grams of neon and argon into moles of both. I just showed this step so you can see where my logic is coming from. I add those 2 together to give me the total moles, which I'm going to need in a second. I then take the moles of each, and I divide them by the total moles. And I kind of just did it all in one step, but you're welcome to kind of break this apart if you'd like to. But then I take the mole fraction, which is what I found in the first step here. that first part with the parentheses, that's the mole fraction. I multiply the mole fraction by the total pressure given, and that gives me the partial pressure of each. So that's the 59.8 kPa and 60.2 kPa. Oh, I forgot to label my units. This should be moles of argon. So this is neon and this is argon. And that's it. That is mole fraction and partial pressure. And that's the chapter. We'll see you in the next one.